Hey guys, so chapter 2, organizing, summarizing data. This time we're going to go over 2.2, organizing quantitative data. So quantitative, something with a quantity. So learning objectives, let's go ahead and get started. All right, so the first step in summarizing quantitative data is to determine whether the data are discrete or continuous. So remember discrete, or I don't think we have gone over. But oh yes, so discrete are things that we could count with our fingers. So whole number values, so 1, 2, 3, 4. Continuous data is like everything in between. So we are able to have half. So that's something more of a measurement. So like the distance between here and school. So we're able to look at like miles, but also feet, meters, inches, centimeters, and stuff like that. So we're able to be a little bit more precise with continuous data. If the data are discrete and there are relatively few different values of the variable, the categories of the data are going to be classes. So just because, similar to what we did earlier, in section 2.1, we don't want to put everything in its own category, especially if we're looking at a bunch of different numbers. We're just going to have a bunch of different categories. It's going to look worse than the raw data itself, and we want to make it a little bit more organized. So what we do is we use classes. So classes will be the observation as a qualitative datum. So if the data are discrete, but there are many different values for the variable, or if the data are continuous, the categories for the data, the classes, must be created using intervals of numbers. All right, so looking at this data right here, the manager of Wendy's fast food restaurant wants to know the typical number of customers who arrive during the lunch hour. The data in table 8 represent the number of customers who arrive at Wendy's for 40 randomly selected 15-minute intervals of time during lunch. For example, during one 15-minute interval, 7 customers arrived. So looking at this very first value right here. So 7 customers arrived within the first 15-minute interval. 6 customers arrived within the next 16 or 15-minute interval. And at one point, 8 customers arrived within a certain 15-minute interval. So looking at this, data is a little bit sporadic. So what we're going to do is organize it. So here the data isn't like too crazy, so we don't have to have like a range of values. So all we're going to do is organize it in its own number. So let's look at the smallest number, or let's see. So organizing this with each of the numbers. So the smallest number is 1. So we could even start off with 0 if you wanted to. So let's say 0. Hold on, let me get a different. There we go. So 0. And the largest number, we kind of just cheated, but the largest number I see is this 17 right here. Not 17, 11. So we're going to go up to 11. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. 12, just because we threw that 0 in there too. All right, the first one is 7. So what I'm going to do is go down each column. So starting off with 7, I'm going to put a check mark for 7, 5, 2, 6, 2, then going up to 6, 6, 7, 5, 2. Next one is 6, 6, 1, 5, 9. Next one is 6, then 11, 2, 3, 4, 2, 3, 7, and then going up to 4, 4, 4, 7, 5, then 6, 5, 8, 5, 9, 2, 7, 2, 4, 8, then 6, 6, 6, 6, 5. All right, so now that we have all of those values, let's find the frequency for each of them. So we didn't have any 10s, doesn't look like, no. All right, so for 1, we had 1. For 2, we had 6. 3, we had 1. 4, we had 4. 5, we had 7. 6, we had 11. 7 had 5. 2, 2, 0, 1. And now it's safe to just erase these the first one and the last one. All right, so again, we have the number of customers, the tally marks, and the frequencies. And now that we have our data here, let's get our relative frequency because we're kind of experts at that now. This was the number of customers. Frequency and relative frequencies. And remember, our relative frequency is parts of a whole. So what we could do is add all these values up and see how many we have. All right, let's do a quick add. So 1, 6, that's 7, 8, 12, 19, 19, 20, 30, 35, 37, 39, 39, and 40. So the total ends up being 40. And that means that each of these is going to be divided by 40. So let's do this and get a calculator. And for that first one, we have 1 divided by 40. 1 divided by 40. So that's 0.025. The next one is going to be 6 divided by 40. 0.15. Then again, 1 divided by 40 is 0.025. 4 divided by 40, 0.1. 7 divided by 40, 0.175. 11 divided by 40, 0.275. 5 divided by 40, 0.125. 2 divided by 40, 0.05, 0.05. 0 divided by 40 is going to be 0.00. 1 divided by 40 is that very first one, 0.025. And now that we have that, if we really wanted to, we could add all those numbers up together, but we know that that's always going to be 1. And let's get 3 decimal places for each of these. And there we go. So that's our relative frequency and everything. So now from here, what we could do if we really wanted to, we could create a bar graph. We could create a relative frequency bar graph, a frequency bar graph. We could even do Pareto if we wanted to. Doing a Pareto graph, bar graph, is not going to be beneficial to us because we do have a ranking with these values. So let's go back to the stuff that we did before. These we really didn't have to rank because back doesn't have a value to it. Here, 1 does have a numerical value to it. And 10 has a numerical value to it, 11 has a numerical value. So would it make sense to put 6 in the very beginning when 6 already has a place for itself, right? All right, so now that we have that, let's get our data over here. All right, we found the frequency, relative frequency, and everything. So the largest amount of times that are the most frequent number of people that go through a drive-through in a 15-minute interval is 6. So on average, in a 15-minute interval, 6 people will go through that Wendy's drive-through during the lunch hour. All right, so now construct a histogram. So a histogram is very similar to a bar graph, but it's going to be just a little bit different. A histogram is constructed by drawing the rectangles for each class of the data. Height of the rectangle is each of the frequencies or relative frequencies, so that's not different from a bar graph. The width of each rectangle is exactly the same. So that's exactly the same as it was with the bar graph. The part that is different is going to be this last part. The rectangles touch each other. So over here where the rectangles did not touch each other, so notice how there was a lot of space between them here and here, just to differentiate between each of these values. With a histogram, all of those values are going to be touching. So we're going to have bars touching in this one. All right, so let's do the same thing here. Let's take it to Excel really quick. All right, same thing we did earlier is let's get our table. There we go. So let's grab this frequency table, Command-Shift-5, so that way I could take a snapshot of it. Beautiful. And let's get Excel on here. Okay, now that we put it in into Excel, so remember all I had to do was insert data from table. I took a snapshot of it, but I'm going to take this time to go over a couple of things just so we get them like locked into our brain. So remember total. In order to get the total or the summation of all of these, we're going to hit equals so that we could tell Excel that we want to do some sort of action. Sum, so we want to add all these values up or take the summation of all of these values, and we're just going to highlight everything we want to add together. So all of those values, perfect 40, which makes sense because they did have 40 different 15-minute intervals, and relative frequency, we get it from the value itself. So the value of 1 customers per 15-minute interval. Same thing over here. The value of 7 customers per 15-minute interval ends up being 5. So 5 divided by that 40. So each portion of itself. So equals this value here divided by this value over here. So the one value that we don't want to move around is going to be this one. So we're going to put $signs in front of it. And we're going to grab this corner here and bring it all the way down. It adds everything up for us. Perfect. So now that we have this relative frequency, we have the regular frequency, let's work on a histogram. So number of customers and frequencies, we're going to highlight that. Insert. And this time we're going to look at frequencies. So, or not frequencies, we're going to look at histograms. So, actually, let's go over here, insert, come back here. Let's do these values and see if we could change it. So switch charts. We want columns, but we want. Okay, starting over, we have our data. So the number of customers, the frequency over here. We have it highlighted. Let's insert. Let's get this right here. Even though this is a bar graph, this isn't a histogram. What we could do is grab this information. It already has like our number of customers down here. It has a frequency right here. And in order to turn this into a histogram where the bottom parts are touching, that's the only difference between a bar graph and a histogram. We come right over here, do this gap width. Let's get rid of the gap. So we want 0 gap. And now we have this gorgeous histogram. So a histogram that relates all this material right here. So we have, so for one customer, we only have a frequency of 1. So we have 1 right here. And again, you could kind of choose a different look right up here. So this one actually shows the frequency up on top, just like we talked about earlier. This one is a frequency of 0. I don't know if you guys could see that, but you could very lightly see that 0 that they put right there. But yep, there we go. That's our data table. Oh, there we go. So we could also do the same thing with relative frequencies. So let's get rid of this chart. Let's hide this. We don't want to delete it. Let's just hide it. So that way we could highlight these two right here. And with this insert, let's do the same sort of thing. This time we're going to do relative frequency though. So we have these charts. Let's click on the actual bars of the graph, come over here. We want 0 gap to turn it from a bar graph into a histogram. And there we go. So now we have our relative frequency. The highest value that we have is this one right here, 0.275. So we went up to 0.30 here. Again, 0 for 10. So a frequency of 0 for 10 here, which means a relative frequency of 0 as well. And there we go. So that's our graph. That's how we could get a histogram here on Excel. And let's continue. Right, caution, the rectangles in a histograms touch, but the rectangles in a bar graph do not. So that's the difference between a histogram and a bar graph, only difference. Now we're going to organize continuous data in tables. So organizing continuous data. All right, so classes are categories in which data are grouped. When a data set consists of a large number of different discrete data values, or when a data set consists of continuous data, we must create classes by using intervals of numbers. So again, we don't want a huge long table with a bunch of different values if it's not going to organize the data for us. So what we do is we range things from a smaller number to a larger number. So here, age 15 and 19, instead of having the ages from 15 all the way up to 54, instead of writing like 15, 16, 17, all the way up to 54, we're able to organize it in these classes. So the first class would go from 15 to 19. Second class will go from 20 to 24, 25 to 29, so on and so forth. All right, so table 10 is a typical frequency distribution created from continuous data. The data represents the number of mothers in the United States, age 15 to 54, who had their 4th child in 2016. So how many people had their 4th child in 2016? So 443 had 443 women aged 15 to 19 had a baby in 2016. 101,070 women aged 30 to 34 had their 4th child in 2016. So on and so forth. Let's see. All right, so now we're going to talk about the classes themselves. So the lower class limit of the class is the smallest value within the class, while the upper class limit of the class is the largest value within that class. So lower class limit here is going to be 15. Upper class limit is going to be 19. So the smallest person or the youngest person in this class would be 15. Oldest person in this class would be 19. Or you could even think of it as like 19 years old, 11 months and 30 days or 29 days or 28 days, however you want to think of it, depending on the month. So that's how old these people are, and continuing on to the rest. Let's see, the lower class limit for the first class in the table is 10, or in table 10 is 15. The upper class limit is 19. The class width is the difference between the consecutive lower class limits. So consecutive lower class limits. So what we would do is look at the difference in age between 15 and 20. So 20 minus 15 would give us 5. 20 minus 15 would give us 5. So this is a class width of 5 years. So even though if we subtract these two, it's only 4, there's still 5. There's 15, 16, 17, 18, and 19. So 5 different years or ages fall into this. And these are always going to be consistent all the way down. So a class with the 5, so we add 5, get this one, plus 5, 25, plus 5, 30, plus 5, 35, plus 5, 40, till we get to the very, very end. Another rule of thumb, another fun fact is this right here too. So 19 plus 5 gives us 24, 24 plus 5 gives us 29, 29 plus 5 gives us 34, plus 5, so on and so forth. All right, so one exception to that requirement is of equal class widths occurs on open-ended tables. So if we were to say, let's kind of look at this over here. If we were to say this like 15 to 19, 20 to 24, 25 to 29, and we keep going. If we look at this right here, 24, and then this next category, if we label it as 20, or I'm sorry, not 24, 55 and older, then it would give us a completely different range. So again, if we looked at this value and we said 54, let me try to make it a little bit different. If we said 55 and over, barely see that here. So coming over here, we said 55 and over. One thing we're doing is we're not keeping up with that part. So like if we add 5 to this, 49 plus 5, 54 plus 5, it should be 59. But if we go and over, it's counting every single person over the age of 55 that had a baby. So even though there really aren't going to be that many people that have babies over the age of 55, it's still possible. And you're still able, yeah, look it up. I actually looked it up the other day. I think there was a lady that was 65 or 68 years old and had a baby. But that's besides the point. So she would actually fall into this category of 55 and over. So that's the only exception. And if we also said younger than 15, if we looked at it that way too. So younger or 14 and younger. So 14 and younger could fall into that category too. So looking at 55 and over, 14 and younger, those are the only two exceptions when we have those class limits. And they give us that example right here too. So they did the over part, so 25 to 44, 45 to 64, 65 and over. So we're looking at all of those different ideas there. All right, so now looking at this data set. So the data in table 12 represents a total fine, including late penalties in dollars for simple random for a simple random sample of 15 parking and camera violations in the city of New York. Construct a frequency and relative frequency distribution of the data. Do they give us rules? Yeah, they give us rules. So to construct a frequency distribution, first create the classes of equal width. Table 12 has 50 observations that range from 65 to 322. So let's take a look at those. What we're looking for is the smallest value. So I look here, the smallest value in that first column is at 147. The next one has a smaller value of 125. Next one has smaller value of 123. The next one, the smallest value is going to be 155, but 123 is still the smallest. 210. All right, keep going on that next one. 24, no, close, but not yet. 190, 127, 124. 121 is the smallest one in this column, which is smaller than the one in the previous column. And we keep going. The next one, not smaller, not smaller. And the smallest value that I could see is at 65. So that looks like this one's going to be the smallest value. And now let's look for the largest value. So the largest value in that first column, 227. Could we beat that? 256 is larger. 262 is larger. 271 is larger than 262. 325. Do we have larger than 325 or 322? Sorry. 322? No, looks like that's the largest one. So in all the columns, so 322, and that's the numbers that they got right over here. 322.16 and $65. So the smallest $65, the largest 322.16. All right, so we decide to create the classes such that the lower class limit of the first class is 50, because we want to make sure that we catch for sure that 65. So if our smallest value is here at 65, making sure that we catch that limit, we go a little bit smaller, so that's why we say 50. So 50 and the class width of 25. So that seems like a good way to start. So we could start with that. And let's take it to the notebook. Okay, so like we said, the smallest class value is going to be 50, largest class value, so we're the smallest data value is 65, largest data value is 322.61. So let's grab our notebook and write that down just so we have it written out somewhere so we could kind of see it a little bit better. So range, so the range, the smallest value goes from 65 and we go all the way up to 322.61. All right, so we want the first class to start. So start at 50, and we want class width of 25. So now that we have that, we could use that to construct our table. So remember, we're going with class limits of our lower class, our very first lower class limit is going to be 50. And we're going to continuously add 25. So let's work with the smaller, our lower class limit. So 50 plus 25 is 75, plus 25 is 100. Then we have 125, 150, 175, 200, 225, 250, 275, 300, 325. And what I want you to notice is 325 is going to be the lower class limit. So that means that everything above or everything in this category is going to start with 325 and go forward. Notice that our largest value is 322. So we actually don't even need this one, but just for laughs and giggles, so we don't mess anything up, let's keep it right here. All right, so remember all of this data is coming from money. So we're going to be specific to 2 decimal places. So that means within this class limit, if this one starts with 75, let's remove 1 penny from that and write that number here. So 75, removing 1 penny is going to be 74 and 99 cents. So $74.99. So that way, if we have something that's $74.99, it's going to go in that first one. But if it's $75, it's going to go in that second one. So now we're going to do that and add 25 to each of those or subtract 1 penny from the previous number. So we could start with that. So either adding 25 to this. Let's go ahead and cheat a little bit. So there we go. All right, cheating just the tiniest bit. What we're gonna do is 74.99, and we're going to add 25 to that. So that gives us 99. So through $99.99, we're gonna add 25 to that. So 124.99. Hit enter and it plus 25 again. 149.99. 174.99. 199.99. 224.99. 224.99 plus 25. We continue to do this till we finish. And adding 25 to that. All right, so now with all of this, we're able to see these, and now we're able to categorize all of the data. So the very smallest value that we have is 64. So that one's definitely, that one has a place right here. The largest data value we have is 322.61. And that's going to fall into this category right here. So we have a home for each one of these. Now we're going to do the same thing that we've been doing and just grabbing that data and finding a place for it. So doing little tack marks. All right, so for the very first column, 121. So for this value right here, 120 or 211 will go here. 105 goes here. 220, 227 here. 105 here. And at this point, you could either stay and continue counting them with me, or actually I'll do this off camera. So we're just putting each and every single one of these in a home. Go ahead and pause the video and do this on your own, and then we could compare notes here in just a minute. Okay, so I did this, and this is what I ended up with. Those are our tally marks. So let's go ahead and write all these numbers down. So we have a value of 1 here, 0, 5, 2, that's 7, 10, 5, 4, 10, 13, 4, 5, 0, 1, 0. All right, so with this very last one, we could actually delete that one or erase this one because we don't have anything there. And it's kind of like having either a 0, 1, 2, 5. So that's 125. You don't need a place for that 0. Or also like saying 0.2000. So that's just like saying 0.2. Right? So what we could do is just delete this last row. So you could delete this last row because it's not exactly needed. So this is going to be our table, and let's see what we should do next now that we have that. Actually, we're kind of experts at this now, right? So this is our frequency. So this is our classes. This is our tally marks. This is our frequencies. So our frequencies. And now with this, we could get our relative frequencies. So relative frequencies, we could use a calculator, or we could use Excel, whichever you want to use is fine. But it's always going to be the sum of all of the frequencies, and each of these values divided by the sum of all frequencies. So if we add all these numbers together, we should end up with the same amount of the same numbers that we have right over here, which is 1, 2, 3, 4, 5, and columns we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we should have 50 when we add all these together. So 1, that's still 1, 8, 18, 23, 27, 30, 40, 45, I'm sorry, 44, 49, 49, and 50. So 50, so 1 out of 50, it actually makes this really easy to find the relative frequency of. So 0.02, 0.14, 0.20, 0.1, 0.08, 0.26, 0.08, 0.10, 0.00, and 0.02. And the different one is this one. And there we go. That's our relative frequency. Again, if you add all those numbers up, it ends up equaling to 1. And there we go. So that's our classes. Remember, our lower class limit is going to be the smallest value that we have in that class. Upper class limit is going to be the largest number that we have in that class. Class width is how many different values jump from this to this, or how many different values we have in each of the classes. And there we go. All right, let's see if we missed anything. So the choices of the lower class limit in the first class and the class width were rather arbitrary. So we don't really have to, it's not an exact science, but some things do look better than others. Like you don't want just 2 classes, right? You want to have a good dispersion of the classes so that way you could see a little bit or see what happens within each of those classes. Yeah, so there is not a correct frequency distribution for any particular data set. However, some frequency distributions can be better illustrated or can better illustrate patterns within the data than others. So construct a frequency distribution in somewhat of an art form. Use a distribution that seems to provide the best overall summary for the data. Guidelines for determining the class limit for the first class and the class width. So this isn't, again, this isn't exact, just kind of like a rule of thumb of how you can get started with these. So first, choose the smallest observation in the data set or a convenient number slightly lower than the smallest observation. So the smallest observation in the previous example was 65, and we started out with 50 just because it looks like a nice number to work with. Then determining the class width. So decide the number of classes that you want. Generally, there should be between 5 classes and 20 classes. Again, that's more of like, it's not an exact science. Some classes do represent the data a little bit better than others, but it's not going to be exact. So for smaller, or for the smaller the data set, the fewer classes you should have. So for this one, we didn't really have too many. We only have 50 different values. So we were able to get away with just having, I don't remember how many we had. What was it? Like 8 classes. So yeah. All right, so yeah, there we go. All right, so now determine the class width by computing these numbers. So the largest data value, smallest data value, and then the number of classes, and that's going to give you the class width. So it's going to kind of be a little bit different. So you always want to round up. So you want your class width to be just a little bit larger than whatever this number is. Again, not an exact science, but just a good way to start. So round this value up because you want the class width to be just a little bit bigger because you are going to catch like a little bit before the smallest data value, a little bit after the largest data value, just so they all fit into their bins. For example, using the data in table 12, we obtain the class width of, oh, and we also want to have these full data values. So that should be a minus in the middle right here. That should be a minus right here too. Yeah, so when we subtracted those two values, so 322.61 minus 65, the largest value, largest data value minus the smallest data value, we divided by 11 because I wanted 11 classes or roughly 11 classes. And they saw that 23.419, that was the result by that computation there. So 23.419 isn't a pretty number. So what they ended up using was that 25. So 25 is a lot easier to work with than that 23.419. Because this is an easy number to work with. So rounding up may result in fewer classes than you originally intended. Rounding down is going to result in maybe a couple more classes than you intended. So again, not an exact science, but you could kind of go off of this. All right, so now constructing histograms of continuous data. So remember with the histogram, we were, all of the data values were touching, so it makes it a little bit easier. So construct a frequency and relative frequency histogram of the fine data discussed in the previous example. Fine as in like parking violation fines, not fine as in like fine and dandy data. That's the way I read it. I'm sorry. All right, so let's erase. Okay. So constructing them, what we're looking at is here at the very bottom, we could kind of zoom in and see that our class widths, we started each of the markings were of our upper class limits. So upper class limit of 50 plus 25 was at 75 plus 25, 100. And we keep doing that until we get to the very, very end. So the last one ended up being up to 325. So remember 325 was the number that we wrote down for this one. It ended up being 325 to 349.99. So looking at that value, 325 ended up being the lower class limit of the following class. It was just a little bit easier to write that number down instead of the 324.99. So not writing that number down, writing that 325 made it flow a little bit easier. Much better. There we go. So we did that. The reason why in a histogram the bars touch is for this specific reason too. So we know that everything in this box is going to be between 250 to almost 275, but it ends up cutting off on that 275. So 250 to 275, not including that 275. But we know that the class limits go from there to there. And that's why they end up touching, because the data kind of flows a lot better that way. You know that it goes from one number to another, and you have that whole number line. So if we were to have the space, notice how there's a space right here. There's that hollowness right here, and that space represents that we don't have any values here. We don't have any values between 75 and 100. So that's what keeps those there. Let's clear that out again. And let's see. So construct a frequency and relative frequency histogram of the fine data discussed. Yeah, so exact same thing. Yeah, there we go. All right, so the next thing we're going to talk about are dot plots. So a dot plot is drawn by placing each observation horizontally, in increasing order and placing a dot above the observation each time it is observed. So really quick, this really good way of displaying qualitative data would be using a dot plot. So I always like using the example of like M&Ms. So if you get a bag of M&Ms, they're all going to be different colors, and you could literally organize them using their colors. So if you had red here, you could literally put a red M&M here, and however many red M&Ms, like physically put them and create your own physical dot plot using those M&Ms. You have blue here, looks a little bit less fuller. You're able to see, like physically see a great representation of what the data looks like by using the actual M&Ms or Skittles or whatever other kind that you wanted to use. All right, so draw a dot plot for the number of arrivals at Wendy's data from table 8 that we used earlier. So we actually have that in our notebook. Let's go ahead and grab it. Let's make a copy of it. Or we could just do it right here. All right, so what we're gonna do is, let's actually do it from raw data. Let's see, do we have it? Oh, no. So give me just a second. What we're going to do is take a picture of the data and we'll come right back. All right, so this is the data from the notes for the number of arrivals at Wendy's. And what we're going to do is create a dot plot. So remember, the very smallest value that we had was 1, largest value we had was 11. So smallest value is 1, largest value is 11. So what we're going to do is draw basically like a number line, putting all of that data right here on the number line and seeing how many we have of each. So let's start with drawing that number line. So starting off with our smallest value being 1, could start off with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. All right, so now for each time that we see any of these numbers, we're going to draw a dot. Let's bring this up a little bit so we don't have to stretch out so much. Perfect. So very first value is 7, and what I'm going to do is go down from here. So 7, then 5, and so on. All right, 7. We're going to put a dot right above the 7, and let's make it a bigger font so that way we could just stop. All right, so 5 or 7, then 5, and 2, and 6, 2, 6, another 6, 7, 5, 2, and starting on the third column, 6, 6, 1, 5, 9, then 6, 11, 2, 3, 7, 4, 4, 4, 7, 5, 6, 5, 8, 5, 9, 2, 7, 2, 4, 8. We have 6, 6, 6, 6, 5. And there we go. We have a dot plot that shows all the different times of this data. So it shows all the data. So one thing that I could do better with drawing this dot plot is having a really good line of where each of these values are. So like as you could see, 2 lands right here for that one here. This one looks a little bit higher, which makes it look as if it's a little bit more important than the rest of those. But as long as you guys keep the data organized, it ends up running a lot smoother than it doesn't. All right. And let's see if I missed anything. Dot plot, cool. And now identifying the shapes of the distribution. So this is really important. This is going to tell us a lot about the data. With a uniform distribution, so figure A is a uniform distribution because the frequency of each value of the variable is evenly spread out across the variable or the values of the variable. So this isn't that great just because there isn't any variability. So we know that all the values are going to end up being 20, and there isn't anything fun about that. There's like we're not able to really measure anything. Everything is exactly the same. So that's not like that interesting there. For this one, it is pretty interesting. So figure B displays a bell-shaped distribution because the highest values or the highest frequency occurs in the middle. So bell-shaped, what they're talking about is this right here. So it looks bell-shaped and not bell as in like ring, ring, little bell. Bell-shaped as in this is what the data looks like. So if you were to see these values, kind of put a dot in the middle of each of these classes. I didn't really draw it to scale, not 100%. But if you were to put a dot within each of those classes and kind of draw it, it represents what we call a bell-shaped or a normal distribution. So we would say this is roughly normally distributed. I don't think it says that here. Figure B displays a bell-shaped distribution because the highest frequency occurs in the middle of the frequency tail, off to the left and the right in the middle. That is, the graph looks like the profile. Oh, I guess they are talking about a bell. Okay, but that's what they're talking about when they say bell-shaped. The distribution in figure C is skewed right. So I know the majority of the data is on the left, but what we're going to represent is we're going to see this. There is more data to the right side of the middle. So I'm counting this as the highest point. There's more data to the right side than there is to the left. So notice the left is only representing that part. The right is representing all of this right here. So this one is much larger if you look at the one on the right side. And you guessed it, when we have right skewed, we also have left skewed. Left skewed, remember this is the tallest value here. That's where majority of the data is. That's where the center of the data is. There's more data to the left of that value than there is to the right of that value. Notice how the left tail is a lot larger than the right tail. So this is left skewed. Caution, we do not describe qualitative data as skewed left or skewed right or uniform. So remember, qualitative data, if we were to look at the M&Ms, so if we had red M&Ms, blue, brown, and green. Can't think of any other colors right now. But if we had red M&Ms, remember we're looking at data here. So majority of the time there's going to be more brown M&Ms. The order in which we put these in does not matter. So we can't switch red and blue and say that we have a bell-shaped curve. We can't do that. So it's not going to be realistic for us to say that. So our qualitative data does not have any sort of uniformity. Like we can't say that it's uniformed or left skewed, right skewed, bell-shaped, specifically because we could rearrange the order. The characteristics of the graphs actually just talk about like the characteristics, right? So when data is organized from like least to greatest, and then we have some sort of pattern, then we could comment on it. So it is important to recognize that data will not always exhibit behavior that perfectly matches any shapes of the given previous figures. To identify the shape and distribution, some flexibility is required. So in addition, people may disagree on the shape since identifying shape is subjective. So basically, if I show you this graph right here, some people might say like, okay, well, if this value is right here, I see slightly more over here on the right side than I do here on the left side. So this must be right skewed. Whereas another person could look at this and say, oh, this is uniform. This is bell-shaped right here. Statistics has a lot to do with just the way that we're looking at the values, not so much it being an exact science. All right, so looking at this data right here, so the figure displays the histogram obtained from the previous example of the fines for the fine paid for parking and camera violations in the city of New York. Describe the shapes. So looking at this, we can't say it's left skewed. We can't say it's right skewed because we do have that missing value right here in the middle. Majority of the data is here in the middle. So let's see. So since the histogram looks like figure B, the distribution is fairly symmetric. However, it's not bell-shaped. So remember, bell-shaped, we have to kind of see that whole bell part right there. And there we go. That wraps up section 2.2. If you guys have any questions, please let me know. Good luck.